This segment we're going to talk about thermodynamic cycles and some of the simplifications that we can make to be able to analyze these cycles easier. So a thermodynamic cycle, you may remember from Thermo 1, this is a series of processes in which the initial state and the final state are exactly the same. So for example, say you've got 4 different states. Well, you may have a process from 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. So that state 1 is the final state and it's also the initial state. If you need a review, I've made all the videos from Thermo 1 available to you, and so there is a video on thermodynamic cycles if that would be helpful to you. We'll talk about a couple of different types of cycles. One will be power cycles, and that's if you're transferring heat from a high temperature reservoir to a low temperature reservoir and you're converting some of that thermal energy into work. That would be a power cycle. There's a review video accessible to you as well. A refrigeration or a heat pump cycle does the exact opposite. It transfers energy heat in the direction that it doesn't want to go, from a cold temperature reservoir to a high temperature reservoir, and that requires some amount of work input or power input. And there's a review video as well for you if you need that. So we'll talk about power cycles first, and we could divide that up depending on what the working fluid is doing, what phase it's in. If it stays in a gas phase, we call it a gas power cycle. If it goes between a gas phase and a liquid phase, then we call it a vapor power cycle. And we'll focus first on the gas power cycles. We'll talk about an Otto cycle, which is used to model a gasoline engine, diesel cycle, and a Brayton cycle. And we'll talk about some different things that we can do to Brayton cycles to increase the thermal efficiency of those power cycles. Real cycles are very complex, and so as engineers, we like to make our lives as simple as possible. And so we're going to talk about some of the big assumptions that we can make to make our life easier, make these cycles easier to analyze. So these are called ideal cycle assumptions, and they are assumptions that we might make for power cycles, not just power cycles and refrigeration and heat pump cycles, not just gas power cycles. So the first assumption that goes in there is that there is no friction, no mechanical friction and no fluid friction. And fluid friction is the thing that would cause a pressure drop. So if you're looking at, say, pipe flow from state 1 to state 2 here, well, you wouldn't have any fluid friction, so the pressure wouldn't drop. Another place that you might see this is within a heat exchanger. So here we've got a direct contact heat exchanger. You've got a hot fluid coming in at 1, cold fluid coming in at 2, and they're mixing together and coming out at some temperature in the middle. And if there's no fluid friction, then maybe those pressures are all going to be, all those pressures will be equal. And then the other type of heat exchanger that we'll talk about in this class, or that we have talked about at least in Thermo 1, is an indirect contact heat exchanger. So maybe you've got a hot fluid coming in at 1 and it's coming out at 2 after crossing over this cold tube or set of tubes. And so if there's no friction, fluid friction, the pressure at state 1 and 2 should be exactly the same. And then if you look at the pipe that's going through there from 3 to 4, there shouldn't be a pressure drop from 3 to 4 due to fluid friction either. If you need a review on heat exchangers, there is a video available to you. All right, so no fluid friction, no mechanical friction, and we also consider that all processes are reversible. So if you have a closed system and you're calculating boundary work, you have an equation for calculating boundary work for a quasi-equilibrium reversible process. If you need a review on that, there is a video on work available to you as well. The other place that that this will come into play is when we talk about turbines and compressors and pumps, so open systems. These are all devices that are typically insulated, and a process so if we model those processes as adiabatic, so Q is equal to 0, a process that's adiabatic and reversible is also known as isentropic. And so all of those devices would be assumed to have an isentropic efficiency of 1. If you need a review, there's a video on turbines, compressors, and pumps, isentropic efficiencies, and also steady flow reversible work, which is really useful when you're talking about pump work. And then the last ideal cycle assumption is that heat transfer is negligible where you don't want it to occur. So any connecting components, turbines, compressors, pumps, heat exchangers. Of course, heat exchangers, you do have heat being exchanged between the maybe the hot and the cold streams, but if you consider the entire unit as a whole, those devices are insulated, and so you don't have any heat transfer across the boundary. We could talk about deviations from the ideal cycle, and we will definitely talk about isentropic efficiencies that are less than 1, which would be due to irreversibilities, or if we considered heat transfer, could be due to that as well. Typically in this class, we're considering it to be due to irreversibilities within the system. You could also calculate pressure drops due to fluid friction, and this would require you maybe to use a Moody chart. So if you've taken or have taken or are taking fluids or heat transfer, this might be familiar to you. We won't consider it really in this class, but it is something to at least to know that you could use if you wanted to, if you needed to calculate pressure drops. And you could also consider heat transfer across the components where you didn't actually want it to occur in the first place. So, well, as you can see, there is a lot that we have to do this semester. We've got a busy semester ahead of us. Let me know if you have any questions, and thank you for watching.